Before Isaac Newton, the movement of things was explained by God and angels making things happen, for example carrying the moon round Earth, or else the inner desire of objects to rise, sink, or do whatever. Newton got rid of all that stuff, saying scrap that big chap, the motion of anything becomes understandable and obvious once you see the forces acting on it. With this knowledge, that knowing the forces meant you could design parts to move and work in completely predictable and designable ways, then machines could be built, and the Industrial Revolution could happen. That Big Isaac was British is one of the reasons why Britain industrialized first. These final 2 videos in the motion topic, people find harder. Watch and re-watch them as many times as it takes. Each re-watch, a little more will go in. Trust the process. And as the P90X legend Tony Horton says, bring it. Newton's 3 laws of motion are how the movement of anything that is moving can be completely explained by how the forces are acting on it. Newton's first law says that if forces are balanced, the object will be moving at a steady speed, or it will be at rest. If you are sat in a chair, the weight force down is equaled by the support force up, and you are at rest. If you're doing a parachute jump, as you are floating down towards the ground, the weight force down is equaled by the air resistance force up, and you are moving at steady speed. If you're pedaling your bike at top speed, the thrust force forwards, from all your pedaling, is equaled by the resistance force backwards, and you are moving at steady speed. If Newton's first law is about balanced forces, then Newton's second law, logically, is about unbalanced forces. If there are unbalanced forces acting on something, that thing will experience an acceleration. For example, if you are pedaling your bike at top speed, but then have one of those utterly minging energy drinks, and you get a burst of effort and enthusiasm to pedal even harder, then your thrust force becomes bigger than the resistance force. The forces are now unbalanced, and you accelerate. Huzzah! There's a formula to do with this idea of unbalanced forces creating an acceleration. Unbalanced force equals mass times acceleration. This is shortened to fun equals ma. But the SQA, being Muppets, miss out the UN part. Anyway, you know already that force is measured in newtons, mass in kilograms, and acceleration in meters per second squared. Whoa, I know this looks complicated, but stay with it. Let's say that the thrust force forwards is 120 newtons, and the drag force backwards is 60 newtons, and the mass is 80 kilograms, and we want to find acceleration. The fun part of the shopping list, the unbalanced force, means the overall effect of the forces acting on the object. So if there is 120 newtons acting forwards and 60 newtons acting backwards, can you see that the overall effect will be 120 minus 60 newtons? The mass m is 80 kilograms and AE equals question mark. The formula is fun equals ma. Numbers go in. If you need a triangle, go for it. I haven't put one in, but if you need one then go for it. Final answer gets units. Here's a bit of a harder one. A car's engine produces a force of 26,000 newtons. The mass of the car is 1,250 kilograms. The force of air resistance on the car is 7,500 newtons and the resistance force from road friction is 1,900 newtons. Calculate the acceleration of the car. At National 5, they are extremely likely to give you the force picture for this, but have a look at the diagram anyway. The car is headed to the right, and the forces are represented by arrows, with the numbers written next to them. There's the shopping list. Again, pay particular attention to the fun, the unbalanced force part. It's the overall effect of the forces that we are wanting for the shopping list. Check that makes sense for you. There's the formula, and there are the numbers having gone in. Can you see what the next line of working is going to be? Sorted. Don't forget those units. Hopefully, you're feeling a little more confident with this Newton's second law formula now. The key thing is to remember that the fun bit means overall unbalanced force. So in the specific example of the bike, the unbalanced force would be whatever number of newtons the green arrow is, minus whatever number of newtons the blue arrow is. For things moving vertically, however, one of the forces that is always acting, and so often needs working out, is the weight force acting downwards. We've met the weight force formula before, in the space topic. The weight force acting downwards on an object is the mass of that object, multiplied by the gravity field strength at the location where the object is. The gravity field strength number for a bunch of different locations is on the data sheet. Weight force is in newtons, of course. Let's do just one example where you have to work out the weight force, W equals mg, before then using Fun equals ma. A high jumper on Earth of mass 65 kilograms produces an upwards force of 900 newtons. Calculate the acceleration. They would normally give you the drawing here, but you might have to put the force arrows on the outline of the object and write their values next to the arrows. Of course, we haven't yet worked out weight force, so at the start this would just stay as W. We know that we will end up using the formula Fun equals ma to find the acceleration. But in order to find the overall unbalanced force, Fun, we need to first find the weight force, W. So we do the calculation W equals mg. See? Now we are able to find Fun, the overall unbalanced force. Continuing the shopping list, we can then write out the formula Fun equals ma, then put the numbers in, do the maths, and remember to include units with the final answer. You're doing grand, but there's some more to do yet, so why not go back and watch all this stuff again, so you're super strong with it before moving onwards. Cutesy bicycles are all very well, but a bit more dynamic. An example of Fun equals ma in action is the flight deck of an aircraft carrier. A number of ex-physics pupils from here are now doing this stuff in the Royal Navy. Would you? Here's an only slightly less exciting version. A trolley thing gets given an acceleration by being pulled by an attached string, draped over a pulley and tied to some masses. The weight force on the mass provides the accelerating force on the trolley, and light gates measure the acceleration A for each Fun value. The experiment reveals that as the unbalanced force, Fun, on the trolley gets bigger, so does the acceleration of the trolley. Who would have guessed? I bet you'd forgotten that we were doing Newton's 3 laws of motion, hadn't you? That's all right. If this was easy, it'd be called PE. Hey you, run around that field, boy. Newton's first law was that balanced forces mean rest or steady speed. Newton's second law was that unbalanced forces mean an acceleration. And Newton's third law really zooms into the point of contact and says that every action, or force applied to something, has an equal and opposite reaction, or force back on it. A few examples makes this much clearer. A blown up but not tied off balloon puts a force on the escaping air, pushing the air backwards. There is an equal and opposite force forwards on the balloon. If you punch a wall, it hurts, because when you put that big force on the wall puts an equally big force back on your fist. If you're in cadets, you know that when you fire a rifle, the rifle puts a force on a bullet to fire the bullet out forwards. But the bullet puts an equal and opposite force back on the rifle, called recoil, which ends up being felt in your shoulder. A rocket engine ends up directing hot exhaust gases backwards, leaving with a huge force. These hot exhaust gases put an equal and opposite force forwards on the rocket engine, which of course is firmly attached to the rocket. Finally, a car tire puts a force backwards on the road. The road puts an equal and opposite force forwards on the tire.